All right. Well, good morning, everyone, or afternoon, depending on what part of the country you're in. Welcome back to the Energy Storage at PNNL webinar. Today's talk, we're looking at capacity expansion planning and how we're looking at long duration energy storage. I think a lot of us are aware of the renewed emphasis we've seen in pushing the envelope of longer duration, going out 10 plus hours, out to even seasonal storage applications. And then how does that fit within the capacity, the planning models that we're developing? So we're joined today by Dhruv, Bhatnagar and Patrick Maloney from PNNL, who will be talking about some of their work that they're doing in long duration energy storage. So I'll do a couple of quick introductions here. I will encourage you during the talk, if you have a question, put it into the chat, and we will have time at the end to get over those questions. So our Dhruv joined PNNL in 2019 as an energy systems research engineer and team lead on the systems planning team of the distributed systems group. Most of his work focuses on emerging energy resource integration through various lenses, namely technical, economic, and regulatory. Currently, Dhruv both leads and participates in projects for the Office of Electricity Energy Storage Program and the EERE Water Power Technologies Program and the Geothermal Technologies Office. His key interests are working in stakeholders to improve the understanding and support the deployment of emerging technologies to address climate change and energy access. Our second speaker will be Patrick Maloney. He also joined in 2019 and currently works on applications of power system planning and operation, transient stability studies, and power system recovery. Prior to PNNL, Patrick completed his PhD in wind energy sciences and policy and electrical engineering at Iowa State University, where he developed methods for long-term generation and transmission planning under uncertainty. Before his PhD, Patrick worked for 4 years in the electric power industry, started his career with Schneider Electric, and then moved to Bonneville Power Administration, where he developed and maintained software for testing protection systems. So with that, I welcome Patrick and Dhruv, and then we'll let you take it away. Thank you.
Thanks, Vince, for the kind introduction. Hi, everyone. Good morning or afternoon, depending on where you are. So one second, I will share my screen. Okay. Thanks, everyone. As Vince mentioned, Patrick and I are going to talk about some of the work we've been doing with capacity expansion planning, and particularly how long duration energy storage fits in with our capacity expansion planning, and how we think about long duration energy storage in future grids. As part of our team, we have Patrick, myself, Shinda Shindaki, Saptashi Bhattacharya, Abhishek Samani, Abhinav Venkataraman, and Ziting Wang. So getting into it, I will talk a little bit into, I'll provide a little bit of a motivation, background, talk a little bit about our modeling approach, and talk a little bit about how we look at capacity expansion planning and how that differs from other sort of grid planning that maybe is more typical. And we'll also talk a little bit about how our approach differs from those of others who are in the capacity expansion planning space. And then Patrick will talk a little bit about some of the analysis we're doing on a case study in California, and particularly in the LA Basin, and thinking about retirements and replacement with long duration energy storage resources. So getting into it, motivation and need. And really the motivation behind some of this work is to think about what does energy storage look like in the near future? So 2030, 2040, 2050, what will energy storage look like given a system that has a high deployment or large deployment of variable renewable resources, and as flexible generation, such as fossil-fired generation, particularly thinking about natural gas, begins to be retired. And of course, this is a question on many of our minds, and it's one of the challenges is we don't really know what that future looks like. There's been a lot of work at DOE, at the PNNL and other labs to think about the future and chart out an expected system topology, expected resource deployments that may meet those carbon requirements. But one of the things that we really are thinking about is how do we get there, and what's the pathway to get to there. So with respect to storage, that means what kind of storage, what kind of technologies, what are their capacities, their durations, and how we deploy them, and where on the grid, where sort of from a time perspective, whether if say we're talking about California and targets in 2040, 2045, does deployment make sense later towards that carbon constraint or that carbon target, or does it make more sense earlier on, and how that interacts with renewables deployment. And then, of course, what's driving the need is our push to cleaner energy resources at the federal level and across several states. So our modeling approach that we're using is capacity expansion planning. Capacity expansion planning is a combination of linear and mixed integer. Linear and mixed integer linear program used to determine optimal timing, size, and location of new investments, both transmission and generation. So this differs from production cost modeling in that we're not just optimizing dispatch and operations. What we're really thinking about is both dispatch and operations, but also investments. And so those play into the objective function, and you're trying to minimize the combination of both. In our case, we're using standard DC power flow. So if you want to really get into sort of dynamics and system characterization on the transmission side, you really have to go into AC power flow. Dynamic analysis and power flow analysis. But that's a step that can be taken once you've done some capacity expansion planning. Capacity expansion planning could feed into some production cost modeling, which could feed into power flow, and we'll get to that a little bit later. So by its nature, capacity expansion planning is a complex modeling effort that requires careful trade-off between models, details, and solve times. So unlike more traditional, unlike production cost modeling, where we're just evaluating 1 year of operations, and we can, take an hourly approach, more, discretely define generation resources and loads, and sort of system topology with respect to nodes. With expansion planning, because you're looking across multiple years, the computational challenges start to add up. So solve time becomes a critical component of that, and as and which is in concert with sort of your computational capabilities. Your representation of storage plays a role in how the duration, how you model it, how you consider its use across different time steps. The intra-year time slice representation, so that is how many operational set points you have in a year, unlike sort of more yearly modeling where you have every hour modeled. If you model every hour in capacity expansion planning, you're going to get quite a large problem. So that's something we'll talk about later on in our presentation. The implementation of renewable resources and the capacity value plays a role, and affects what happens at that 2040, 2045, whenever your expansion planning model is wrapping up, what that looks like, and how you represent that, and also plays a role into solve times. Representation of uncertainty, retirements of units. Those are just some of the key parameters, but there's of course many other characteristics of system operations, and all of those can be modeled similar to other modeling approaches, but they really have to be considered with respect to solve times. So the tool we're using is called GridPath. It's an analytics platform developed by Blue Marble Analytics, who we're partnering with in some of this work. It's an open source piece of software, so it's available for use. We've identified the website below. But something we really like about it is that it lets you do the capacity expansion, but it's also versatile enough that you can leverage the same model for production cost analysis, for resource adequacy analysis, and asset valuation. I'm happy to chat about that more if there's additional questions. So talking about our modeling formulation with GridPath, so starting on the left, objective function costs. So those include variable and fixed costs of operations, fuel costs, generation, resource and transmission investment costs, and penalties such as reserves, policy violations, reliability constraints. All of those sort of fall into costs to the objective function. And then you constrain that objective function with power flow, investments, energy storage, operation sizes, planning reserve margin, other reserve requirements, carbon constraints, and retirements. So as I mentioned previously, excuse me, production cost modeling will do a single year study, we'll do every hour. And so that's the graphic on the top right. In expansion planning, because we're looking at multiple years, we don't analyze every hour. We're doing a subset of hours, and you identify either the best days, the best hours that are best representative of each of your years, and you optimize over those. And so your optimization window is across all of those hours and days across years, as opposed to 87, 60 hours in a year, for example. Moving forward, so we have our model established and what we're going to do, but things we want to really think about that sort of that go beyond traditional expansion modeling efforts are system resilience, equity considerations with resource deployment, and how the expansion model selects resources. And we'd also like to get into thinking about an option value approach. So this goes back to what I mentioned about how storage is deployed, and what increments, what sizes, whether it's deployed early on in the time frame, was deployed later in the time frame. What's the pathway towards meeting a 2040, 2045, 2050 target, and how storage deployment looks in that pathway. So those are a couple of things we're focusing in on in this work. And I think we're going to present some results that are sort of providing a lens into what we're working on, and hopefully we can come back and get into more depth in some of these questions. So as I mentioned, existing other expansion models have considered storage needs in future electric systems, but really what they don't answer, because they're really generally looking out to sort of those long-term futures of zero renewables, or 35% or 50% or whatever the target is. They're looking out towards those end years, and what we're hoping to do is really look at that pathway and how you get there. Another thing a lot of expansion models have done is look at the broader system level, which is certainly valuable and very important and informative. But we're taking a little bit of a different approach and a different lens, and really look at specific jurisdictions and specific areas. So when Patrick talks about some of our modeling, he'll get into the LA Basin area, so greater Los Angeles area, and that's sort of, we're looking at answering some specific questions for those jurisdictions. Some of the other things that we've that provide challenges and kind of go to what I was speaking to about computation time, is a limited ability to model long duration storage, because time horizons are short, and the problem gets quite complicated quite fast. So traditionally, when you're looking at 4-hour batteries, maybe it's less of a problem. But as you start thinking about longer increments of energy storage resources, having more hours or more chronological hours or days that are connected becomes more and more critical, as opposed to some of those separated days, as I mentioned before. The other approach, often expansion approaches are limited by using zonal models. So they identify needs in broad regional contexts and optimize over zones, which is again important and valuable as you think about sort of a larger system perspective. But we're hoping to get a little bit more into depth and really model some of that transmission and look at go beyond the zonal perspective and go into a little bit into the nodal perspective. And then finally, because modeling is what it is, and then the approach that's taken is the lowest cost objective. I think some of the things we want to think about are getting beyond that lowest cost objective lens and think about other questions. As I mentioned, resiliency, which may not be the lowest objective. Lowest cost, meet the lowest cost objective for a resilient system versus a non-resilient system. Think about some of that option value analysis and equity as well. So the case study we're using is thinking about using energy storage to replace peaker plants in communities in the LA Basin. California has ambitious, of course, you all know, California has ambitious energy and environmental targets that already have led to quite a bit of deployment of variable resources, particularly solar, but also wind. And as we move on in time, those requirements get more stringent, and more and more renewable resources will have to be built. And their existing fossil resources, the flexible resources in which they rely on for reliability, will have to be retired. So something will have to take their place. And energy storage, of course, as we all know, is one of those, a critical tool to making sure reliability is met. We've already seen quite a bit of energy storage deployed in California, especially in some of those leveraging transmission connections for some of those retiring plants, but there's still a long way to go. And so for the LA area, for example, there's about 8 gigawatts of low capacity factor peaking natural gas that could theoretically be replaced. And so some of the work we're doing here is to think about how energy storage, and depending on, energy storage could meet that need and could enable those retirements, but what that energy storage would need to look like. So the system under study, we started on the top left with the 3-bus LA model, looking at the CAISO, the California Independent System Operator subzones, West LA, East LA, El Nido. We've actually built that out into a broader California model, building off of the California Public Utilities Commission's resolve model that CPUC, the Utility Commission, uses for some of its IRP work and projections out into the future. We've taken that and added the specificity of the zones within the LA region to really get at answering some of those questions. And so combining those two, we have now a 10-bus model for California. The benefit of being able to leverage some of the PUC work is not insignificant, because there's a lot of stakeholder engagement and efforts that go into determining modeling parameters, what loads look like, what renewable resource looks like, what are expectations of future deployment, what are possibilities for resource selection, and all the above. And so our being able to leverage that has been quite important. Longer term, what we want to do is build off of the California model and build a WEC model, so the Western Interconnect, and again, contrasting with some of the other expansion planning work that's been going on in industry. We're hoping to do a little bit more of a specific sort of nodal approach, and have more details in particular regions of interest. So this is just the graphic on the right is just it's just a highlight of a simplified model that Patrick developed in prior work, where he took a large 30,000 node grid model, production cost model, and downscale that to a 300 node model that could then be used in expansion planning. So jumping to energy storage, there's two ways to model energy storage within expansion planning. One, of course, is or two ways that we're thinking about it. Excuse me. Of course, there's more than this. The first way is pick a duration, and so you're kind of pre-establishing the duration of the storage devices. So say 1 hour, 10 hour, 100 hour. And then you let the optimization determine the amount of capacity to be built. Another approach is you let the model determine both the duration and the capacity. You can set within the model, you can set several storage technology or storage types, modify, set parameters with respect to efficiency, charging, discharge rates, and the above. And then let the optimization choose sort of what it thinks is an optimal deployment approach. And then finally, and this is kind of we've kind of taken in between, we've constrained we've set some minimum thresholds for storage resources, which Patrick will get into, or actually I will get into in the next slide. But we let the model sort of decide between those durations and optimize sort of between the ranges we've identified. And then, of course, it will pick the capacity to meet reliability needs. So the storage options we're using in this analysis are based off of Canada options that Strategy Consulting used in their long duration energy storage for California. They did this for the California Energy Storage Association. And as part of this effort, we're working with them to do this analysis. In this case, just for simplicity, lithium ion is selected as sort of as the base resource, and the other resources are sort of assigned cost multipliers off of the lithium ion basis. So we're using the Pacific Northwest National Lab, the PNNL energy storage cost and performance effort to identify our lithium ion costs. And of course, it also includes cost with respect to flow batteries, pump storage. For those longer duration resources, when we get into 10-hour plus storage, 100-hour storage, we've instead switched to some of these cost multiplier numbers and made some assumptions with respect to round trip efficiency of those resources. So of course, there's no, there is with respect for 10-hour storage, you could potentially use a pump storage resource, you could potentially use flow batteries. There's no commercially deployed 100-hour storage resource, although of course Form Energy is working on theirs, and there's other hypothetical approaches, or other theoretical approaches to 100-hour storage, maybe using hydrogen. There's some work, of course, in gravity storage. All of that's sort of a part of that's been presented as part of or has been discussed with the Energy Storage Grand Challenge and within the storage program at OE. But we're trying to be resource agnostic or technology agnostic and sort of set high level parameters on which to base these resources off of. So that's sort of, hopefully that outlines sort of how we've approached the longer duration storage resources, which Patrick will get into because the model does select them in some of the scenarios we're looking at. So jumping to the next slide, Patrick is going to take it over from here to talk a little bit about modeling.
Can you hear me?
Yes.
Okay, great. So great overview, Dhruv. So we're going to transition to talking more about several scenarios that we've run and the implications of those scenarios for storage investments. And so we have a scenario one, which is a base case. And so we've set it up so there's no retirements and no transmission upgrades. And I should mention the CPUC resolve model, it is typically run as just a generation expansion plan. So this is pretty similar to what they would be using them with no transmission upgrades. Although as we get to the last scenario, we will include some potential transmission upgrades. So the first case is just kind of a baseline to understand what the model looks like and what the battery investments are. In the second case, it's a high retirements case. So we retire all of the natural gas, and it's kind of a forced outage of 8 gigawatts, and that's the table in the upper right for the different areas that make up the LA Basin. So, a lot of gas plants in LA West, quite a bit in LA East, and a little bit in El Nido. Just in terms of the picture in the lower right, the LA Basin is that area outlined in green. So that's scenario 2 is the high retirement case. So all 8 gigawatts are retired during the planning horizon. And then scenario 3, we designed based on the results of scenario 2. So as you'll see, there's a fair amount of load shedding if you force all those retirements out, and we have some limitations on the amount of investments in terms of solar and battery storage that you can put in the LA Basin. And so ways that could be alleviated is potentially more solar. However, in scenario 3, we've chosen to alleviate that constraint by allowing for transmission upgrades from LA West and LA East to CAISO, and then also within the LA Basin. So those are the yellow lines in the picture are indicating the transmission upgrades that we've allowed. And so the lower right is showing maximum investable capacity for those different investments. We go to the next slide. So we're going to go through a couple of results. We have some tables initially that are going to show the investment decisions between 2022 and 2045 for the 3 different scenarios. And then we'll actually look at some state of charge and dispatch plots that kind of help further illuminate the answers or the results that we have. So in this first one, this is scenario 1, it's our base case. I'll make note of this. We restricted the solar investments to be up to 1 gigawatt cumulative over the horizon for each of the 3 areas. And we also restricted the individual battery technologies to be about 24 gigawatts throughout the horizon. So you can see on the left, that's the technologies of investment. So the solar, it basically reaches its 1 gigawatt investment amount, and then there's an emphasis on lower duration storage. So the ES4 is a 4-hour battery, and each of the areas heavily focus on that. And then there's some of the 10-hour battery storage as well. And something that's interesting that Dhruv brought up earlier is that we have constrained the different battery technologies to have certain durations in the planning model. So for that ES4, it can only have a duration of 1 to 4 hours, and for that ES10, it has a duration of 10 to 24 hours. And so something that we're seeing is kind of a common theme throughout the results is that it is, once you choose the technology and the amount of megawatts that you want to invest in, it is always choosing the highest duration that's allowed for that technology, which is kind of it's a result that we didn't know what to expect, but it's kind of interesting that we're seeing that across the board presently. And then the plot on the right, it's not particularly useful for this, scenario 1, but it's good when we compare scenario 1 to scenario 2, since we have some load shedding. But we'll talk about that on the next slide. Go ahead, Dhruv. Thanks. So this is scenario 2, and we'll see some dispatch plots that will help explain the result of this shortly. But in scenario 2, so we've done 8 gigawatts of retirements, and we still have the same resource limitations in terms of generation in the LA Basin. So these results are all LA Basin focused. This is connected to the greater California system, but we're focusing specifically on the LA Basin for these. So you can see previously we had quite a bit more short duration battery investments in 2045. That's the picture on the left. And in this one, it's reduced quite a bit. So I think we had almost 24 gigawatts in each of the 3 areas previously, and then it's quite a bit less than what I think and we'll see it in the dispatch plots. So there's some load shedding in this one, which is indicated in the figure on the right. And so what we think is happening here is that, if you have extra energy or power that you can generate, it's immediately being used to service the load, because there's not enough power to service the load as is. So it kind of attenuates the investment decisions. But again, as you can see, the durations are still maxing out. So it's always choosing 4 hours as opposed to 1, 2, or 3 hours for the battery durations. Okay, go to the next one. And this is scenario 3. So what we did is, in the scenario 3, is we retained the 8 gigawatts of gas retirements, but then on top of that, we allowed transmission capacity. And another way we could have tried to solve the load shedding problem is allow more solar in the LA Basin, but solar, you have to put it in specific areas, and there are some space requirements that maybe are more restricted than where you could put batteries. So we left that limitation on it, but there's multiple ways that this load shedding could potentially be solved, but we chose transmission for this particular scenario. So you can see at the bottom of the table on the left, you get a fair amount of transmission capacity between CAISO and the LA Basin, and then a little bit in between 2 of the areas in the LA Basin. And so something that's really interesting here, and we'll see this on the dispatch plots, is that instead of selecting the short duration storage, it is starting to select the longer duration storage. So it gets a lot of the 100-hour storage, that's the ES 100, and that has the duration of 100 to 200 hours. And then also the ES 10, which is the 10-hour duration storage, and that has the duration between 10 and 24 hours. And again, as you can see, when we allow the optimization problem to choose the duration after you've kind of determined what the power capacity is, it's always choosing that longer duration, which is interesting. And we can show you some dispatch plots now and state of charge plots to understand the battery's operation a little bit better now. Go ahead, Dhruv. Thanks. So this is a state of charge plot. So on the y-axis, that's the energy and megawatt hours, and on the x-axis, that's the hours. So Dhruv had mentioned this earlier. When you run these capacity expansion plans, you really need to reduce the number of hours from 8760 to something smaller. And so for our simulation, for the ones you're seeing right now, we have it's a 2-year and then 37-day hour simulation, where each of the 37 days has all 24 consecutive hours modeled. And then you can see in the legend above, it's a little messy, but I'll explain what the legend is trying to indicate. So it gives the battery technology. So Li_battery is the 1 to 4 hour battery. And then you have the long duration energy storage, or the LDES 10 and 100. And I put the durations there as well, just to make it clear what those are. And then after that, it has the specific area of the LA Basin. And so what you can see, and we also have an aggregated state of charge too, that sort of sums up over all the batteries. So that's the brown is the aggregated state of charge of the system. And then you'll see the different technologies below. And I think this one's useful, but it's most useful to describe in terms of the later state of charges that we'll see. But maybe the thing to kind of keep in mind is there's this area between maybe 150 hours and 375 hours where you see this kind of ramp up of the state of charge of the system with that brown trend. And something that we'll see when we get to the third scenario is that instead of having kind of these up down variation in that trend on the way to getting that really high state of charge, when you have the longer duration storage, you get really smooth charge ups to that figure. But the only other thing to maybe mention here is because we're using a reduced set of hours, the individual hours are actually weighted by a specific number of days on the x-axis. But anyway, I think that's probably all we need to talk about on this one. Oh, go ahead. Yep. And so this is the dispatch plot that corresponds to scenario 1. So that kind of red trend on the top is the load of the system. And then down below, since this is the scenario where there's no retirements, you can see the blue is the natural gas output of the system. It's providing a nice base load. And these are stacked plots. So it's just the energies adding up on the stack plot. So above zero is going to be dispatches and battery discharges. And then if you see below zero on the stacked plot, that's indicating the battery charging up or taking energy off the grid and storing it. You can see the green and the purple are the only two things that are negative or below zero are the batteries in the system. But one thing you can kind of see, so if we look at the green and the yellow, you tend to get a fair amount of dispatch in some of the peak loading time periods of the system. So we do seem to be operating correctly. And also when you see some of the lower dips in the load trend, you tend to see a bit more charging up or below the axis. The space between the load and the dispatches is indicating the imports to the system. The LA Basin, from what we've seen, it does have about a 10 to 12 gigawatt import capacity. So we do see significant imports, and for the second scenario, that space will really indicate both the imports and the load shedding. But for this one, there's no load shedding. Basically, we just see a nice base load scenario plus some storage dispatches. You can go to the next one. Yep. So the second one, it has the load shedding is included in the system, and something that we see because of that is it's really just it's focusing on short duration batteries, and the dispatch or the state of charge is really spiky. So it may be able to store some energy temporarily, but it's going to immediately use it to try to prevent additional discharging. So it's a different characteristic from the first plot or scenario one's state of charge. We can go look at the stacked dispatch. I think I got to be a little bit aware of time here. We got about 6 minutes, but we got plenty of time to get through. We have another 4 or 5 slides here. Go ahead, Dhruv. And so this is the dispatch plot again. We see the load. The white space between the dispatch, or the green and the blue, is indicating this time the imports plus the load shedding in the system. And then again, you can kind of see there's a lot of a fair amount of battery discharge. You kind of see some of the peaks on the high load hours, and then you might see a bit more charging up during the low load hours when you compare the two different trends. We can go, and I think the third one's maybe a little more interesting for the comparison. Yeah. So, and I don't know if we can do this, but so for this one, we have the long duration storage. If you recall, this is where we added the transmission and the retirements to the system. But if you look at the trends, even so, there's the aggregated state of charge, which is brown. But then we also see some of it's the orange and the blue. Those are 100-hour battery state of charges for the entire LA Basin. And you see a lot of it's just a very smooth charge up. And I think something that we're seeing here, part of the reason why we need all this long duration storage in the third scenario is it's really trying to replace the operational flexibility that the natural gas had previously provided to the system. But I don't know, can we flip back? Actually, it might be hard, but if you recall back to the first slide where we showed the state of charge, you still get a lot of these large charge ups, but it's not nearly as a smooth, monotonic increase through time. Yeah, so you can kind of looking at that same area, the brown trend, it's very jagged going up, but I think this indicates some of the differences in how you would operate the system between having a short duration batteries and long duration batteries. Okay. And I might mention one more thing here. We have validated this in certain scenarios. So we had a really good comment while we were analyzing these results. You'll notice the charge up can be slow, but you can sometimes get a very rapid discharge of energy on the system. So this goes back to the comment that I made before. It's that triple asterisk comment in the bottom. Each of these hours, I think there's 1 to 888 hours in our system. It's 37 days times 24 hours a day. But they have a specific weighting in the system. So what we've noticed on some of these very large discharges is those hours actually have, they might have a weighting of actually 20 hours. So it should, in reality, we could stretch out the x-axis. We could, stretch out those time points, and you'd get a much slower, it would look much slower and be more representative of what is actually happening on the system. It's not an immediate discharge. It's just some of those really fast discharges. They're corresponding to time points along the x-axis that are heavily weighted in the optimization formulation. We can jump to I think we have 1 or 2 more slides here we can jump to. Again, this is the dispatch. I think it's just, pretty similar to before. We have the load. You kind of see a lot of charging up during low load and discharging during the high load time periods here. And then you see the effect. The red is the 100-hour energy source. That's really dominating the dispatch in terms of batteries over the 10-hour storage. Go to the next slide. And so, maybe the three takeaways that we're seeing from this scenario analysis, and we're doing a lot more scenario analysis now, is when the system has lots of dispatch flexibility, when it has lots of natural gas in the system, that it can, move up and down whenever it wants to. Shorter duration storage seems to be the optimal solution. However, if you lose that dispatch flexibility in the LA Basin, it seems that the optimization is really selecting longer duration storage to make up for some of that. And then maybe a final point that we have noticed in this is, when you choose a different specific technology and a power capacity for that technology, the optimizer is choosing longer. If you have a window that you can choose the hours between, for like 1 to 4 hour storage, 10 to 24 hour storage, or 100 to 200 hour storage, it really wants to choose that longer duration for the battery storage. One more. I think it is our last. We're coming up. Yeah, I think we'll end right on time here. That's a sample of our work that we've done some of the analysis with, but we do have plans to really try to extend this work as much as we can. I know, presently we have done a lot more work with carbon, but we also want to look at equity considerations. Additionally, we've been looking at a 37-day, 24 hours per day time horizon within each year. We're trying to extend that, but also try to get better representation of consecutive days in the system. Right now we have consecutive hours. Based on the CPUC's data set, it's not clear if we actually have consecutive days right now, but we would like to adjust that so that we can have better representation of the temporal aspects of the simulation. And then we want to do some scenario analysis. So looking at the impacts of operational reserves, carbon constraints, transmission costs, and storage options and costs as well. And Dhruv mentioned this before. A goal of this is, we start off with a 3-bus system. It's kind of easier to troubleshoot and understand what's going on in terms of battery investments. We've extended that to this 10-bus California system, and the ultimate goal is to get this to a nice a WAC-wide system to get a better analysis of the actual interconnection. And I think that might be our last. And go ahead, Dhruv.
Okay. Yep. Thanks, Patrick. I think we just wanted to end on before we get questions and answers. Just wanted to thank Dr. Shook and the storage program for the support of this work, and also wanted to thank our collaborators at Strategy Consulting and Blue Marble Analytics for their insight and their support as well. So happy to answer. I think we have some questions in the chat, so happy to answer those and any more that might come up. And
Yeah,
please feel free to reach out. Oh, sorry, Vince. Please feel free to reach out with additional questions to either of us through email, and would love to engage and collaborate.
One of the questions that came up was when you were talking about the 3 scenarios, and in scenario 3, does the model determine which transmission lines are going to be upgraded, or is that fixed in there, which ones are going to be upgraded prior to running the model?
It's a good question. So what we've done is I would say it's guided. So we don't choose the capacity, but we allow the candidates only in certain areas. So we say you can either choose to put the transmission in these 4 areas or not. We could have allowed that across the system. We put it in those 4 areas because we're really just focusing on the CAISO system, the California system. The CPUC doesn't necessarily do a lot of transmission planning. So we've allowed it to have transmission upgrades in certain areas, but the optimization will choose how much, whether it puts any in or not in those 4 areas. If that makes sense.
Okay. So kind of a follow-up question on that. So when you look at storage systems, you show different scenarios, and some of them had a much slower ramp rate in there. It is kind of, is there a ramp rate that's fixed? You know, a lot of these storage systems do have a different response time. And so I was wondering if that's a consideration too, as you're looking at not the duration, but also the response of that. Is that part that can be incorporated into it, or some of those values fixed within the model?
I can try to answer that, Drew, if you'd like. So I believe the ramp rate is fixed by the megawatt capacity of the system. So if you have a 10 megawatt battery, I think you get 10 megawatts per hour to ramp up or to ramp down. That might be something we need to just double check, but you know, we can even, because it's open source software, we could potentially make that faster or slower. I can see maybe an argument for the slower, but it's a great question.
Yeah, just to add to that, I think, yeah, you can exogenously set those ramp rates in. So yeah, it'll do the whole capacity in an hour because it's an hourly simulation, but if you wanted to slow it down, you could.
Okay, thank you.
Yeah.
So we had another question that comes in. I think it's back to one of the earlier slides when you were talking about the technology and the cost of it.
Mm-hmm.
And it said, you know, we had listed on what's the fixed cost. And so is that fixed cost kind of the total installed cost? You know, it includes all the system, the power electronics, every container, and what it takes to get that energized. I think that's what we track in the cost and performance report there. Or is there a different definition of cost in this case?
Yeah, take that, Patrick.
Yeah, if you'd like me to. So right now, what we're using for the base cost and for that lithium-ion battery, we're using the NREL ATB. I think it's basically like an overnight build cost where they try to aggregate a whole bunch of costs into like what it would cost, and so we chunk that in there. But it is sort of like a one big cost. However, the way the software works, it's actually annualized that cost throughout the planning problem. So there is that, and then there are. You know, for each of the technologies, they have fuel costs. The batteries don't have that, but also they have a variable cost associated as well. But the fixed cost, it is kind of like your traditional fixed cost for a generator plus the capacity cost, or the overnight build cost is what they sometimes call it.
Oh, okay.
Yeah, to add on to that, so we actually switched to the PNNL numbers.
Oh,
yeah,
yeah.
the PNNL cost and performance report numbers, but it's effectively the same thing. So it's like you said, Vince and Patrick, it's the whole overnight capital, all inclusive capital costs is part of the fixed costs, and then there's a separate O&M cost adder.
Okay.
Yeah.
So another one, you mentioned the selection of 37 days in there, and I know you've got it. Is that during a summer peak or 37 days, or is it more random sample, or how do you choose which days are going into the model?
Good question. So I will say this. So we have chosen the same hours that the California CPUC resolve model is choosing. But I can tell you how people typically choose those days is they try to pick up representative days. You can use like clustering algorithms, but they're trying to find out days that sort of have similar loads and like renewable or like hydro outputs, and they'll group them, and then you sort of weight those days in the objective function. But you would definitely want to choose a peak day for that. To really, because the peak days tend to drive the investment decisions throughout the horizon, because you want to make sure you can meet the peak demand of the system. In the future, we are looking at trying to, rather than just use the CPUC's representative days, we're actually trying to look at the full 8760 and come up with our own representative days. And even try to actually see if we can run just a single year with all the hours in the system.
Okay.
But,
and Patrick, you had mentioned the resolve model, I think. So we had a question about how is storage addressed in the resolved model, and kind of the what's the value look like coming out of there if it is?
Yeah, Dhruv, I can try to answer this, but I think we were just talking about this. If you want to take this one.
Sure. Yeah, happy to take that. So, so storage is modeled. I think the elements that resolve the resolve models, or the resolved CPUC models, are for our batteries, pump storage, which I think they've set as 12 hours, and 8-hour flow batteries. So those are the only 3 types of storage resources that are modeled as part of the CPUC process. And they do consider, so I think the question about valuation, they do consider, of course, energy. They consider reserves. Those get incorporated into that objective function. I think the other element that perhaps, and this goes back to the sort of that 37 days question, is that those are not, there might be a couple of contiguous days, but overall they're sort of separate characteristic days. So you can capture the value of a 4-hour resource and maybe even an 8-hour resource, but as you start getting beyond that and really getting into sort of multi-day needs, that can kind of get lost. And so I don't want to say it's inaccurate, but maybe it's not the entire picture. And our use of the sort of that 37 days from the resolve was intentional because we want to be able to leverage all of the work the CPUC has done with sort of establishing assumptions and all of that. But from there, I think what we really do want to do is look at sort of do a sort of more detailed characterization of representative days, maybe multiple days together, so 3 to 4 to 5, maybe multiple weeks together, up to 2 weeks together, and then also run the 8760s to get a better representation, I think, of the value of the long duration potential for long duration storage resources.
And just to add on to that, like I think there's some interesting things, just like what you mentioned, Drew, that we can do with adding new technologies and looking at different adding different hours that maybe the CPUC data set doesn't use. But a really interesting portion of this is trying to look at a local municipality that a zoom in of an area that the CPUC data set does not look at, and not just doing that for this, but trying to figure out how to do it in general. Like how do you when you have these big WEC models that you typically have to reduce down to a certain number of buses, how do you consider like a specific area within that to really understand the investments for that local area?
All right. So yeah, we did have another question come in. It says, how does the simulation duration and computational cost scale with the number of days simulated?
Which is why we don't do 8760s, or not everyone does 8760s right away. Yep.
So it's bad. I think it's so people say exponential a lot, but usually it's not quite exponential, but it's almost there, where as you increase the number of days, the computation time, it's not linear. It's a lot worse than linear. So if you doubled the number of days, you might expect 4 times or 6 times or 8 times the computation time. And so that is one of the reasons why these long-term planning problems, they typically reduce the number of days in the system.
Yeah, maybe Patrick, you mentioned sort of some of the other trade-offs you could theoretically do, and some of the models do, less specificity and sort of transmission or sort of representation of regions or reserves or aggregation of units, etc.
Yeah, all those are great. You can usually when you blow up the model in one particular vector, you may have to scale back in another one. So a lot of times the time is done, but like the geographic size of the system, so how many buses you have, can be done. So if you have a 20,000 WEC system, 20,000 bus WEC system, you may have to scale back a lot in like the time dimension. The other one is number of years. So the number of years, that basically doubles the size of the problem if you double the number of years. So maybe you choose instead of 20 consecutive years, you might choose every 5 years to significantly reduce the computation time. But all of those are ways to sort of scale the model fidelity to match the type of study that you want to run.
Yeah, but then of course you lose the detail in those areas that you've simplified.
Exactly. Exactly.
So I think we've got time for one more. But you know, we're seeing a lot of interest in hydrogen as a long duration storage asset. So can the model accommodate that, or you know, do other things need to happen to start looking at the viability of hydrogen in these planning models?
Maybe I can take an initial crack at it and then Patrick add in. So I guess theoretically the 100-hour storage resource model could be thought of as hydrogen, but that doesn't capture, I think, Vince, to your point, all of the other sort of complexities that go behind that. So there is now, I think that the developer just added a hydrogen module to the tool set. And so we're hoping to incorporate that, and that'll include considerations about hydrogen production, other hydrogen demands such as maritime transportation or big long distance shipping, for example, and then also hydrogen use for storage. And I think that'll get a little bit of a better representation than saying a long big battery or big storage resources, potentially hydrogen, because then you lose if you do it, if you just use the battery representation of it, you lose maybe some of those, or the storage battery representation. You'll lose some of maybe the efficiency. You lose some of the other demands and external demands of it. You lose some, characteristics of the need to produce hydrogen, because unfortunately, unlike maybe a battery system, there's much more involved than a single location for hydrogen to be able to use hydrogen.
Good answer. I don't have anything to add to that.
All right. Well, Dhruv, Patrick, thanks again for the webinar. Really appreciate it. I learned a lot from doing this, so really appreciate that. Laura, do we have the slide on the next presentations? There we go. So yeah, hopefully in 2 weeks you'll be able to join us. Let's see, I think actually Christine Holland will be talking about electric vehicle and integration of EVs into the grid. That'll be August 25th. And then on September 8th, Mark Willey will be talking about the challenges of supporting the US energy storage industry, especially on lithium ion batteries. And then on September 22nd, Emily will be talking to us about machine learning and how that plays a role in energy storage. So thank you again for your time today, and look forward to visiting you, seeing you again on our upcoming webinars. Thank you.